right. Let me start my counter. All right. So I'll be talking about this funny title, exploiting the not so misuse-resistant AES-GCM API of OpenSSL. I showed that to my mother. She was in Uzbekistan. She said it's exactly like people talking there. So that's me. I'll not be presenting myself anymore because I have too many content. So I'll be establishing a few concepts that I think you require to understand what we'll be talking about. Then we'll talk about the concept of misuse resistance. Some of you might know it, some might understand what that means, but we'll cover it. Then we'll talk a bit of the OpenSSL bindings in Ruby and PHP specifically. And then we'll see how the issue I want to talk about can be identified and then exploited. And the exploitation part will cover both ciphertext forgery and decryption via what I call a format validity oracle. And then we'll talk about some limitations on that, and then question marks, and then conclusion. So let's set the table first. AES-GCM, what that is AES is a block cipher. Let's not cover that. GCM stands for Gaulois counter mode, which mixes two things. The counter mode, the classical counter mode that changes a block cipher to a stream cipher effectively. And then the Gaulois field hash function, G-hash, sorry. So this one computes an authentication tag, and that's what provides integrity to the ciphertext we'll be sending. So key concept first, CTR mode. So basically, there's a nonce, a counter, it's combined. It gets encrypted with the secret key. It outputs a key stream. The key stream is XORed with plain text. And then, well, that plain text that has been XORed with the key stream is our ciphertext. You've seen this on Wikipedia. I've taken it from Wikipedia. I prefer this version I've changed. The key stream blocks are cleaner to see. Basically, we take what we need of the key stream, we XOR it with a plain text, and we get the ciphertext out. So obviously, because it's just a XOR operation, any XORed value in the ciphertext will match a XORed value in the plain text. So CTR alone is not safe to transmit data. So how do we fix that? We have an integrity check that will be done with the authentication tag. So after CTR has been done, we have a ciphertext, additional auth data, whatever, and it's sent to the G-hash function. This G-hash function derives a key from the secret key, the encryption key. So it derives the key, uses that key, puts the whole thing in G-hash, and we get an authentication tag. This is recomputed from the ciphertext, validated before decryption, so that we can know whether or not the ciphertext was modified. This alone makes it integrity safe, whatever. There's an integrity check. It's similar to a CRC32 in a sense that it's been modified. It's just that here we need knowledge of this encryption key to compute that tag. Now, the whole point of that talk is to have an issue to talk about. So the misuse resistance concept, so basically when a component is designed to make implementation failures harder to happen, you might have ideas in mind, we'll get to this, but basically encryption normally is safe. The theory behind it is safe. It's usually an implementation flaw that breaks what we've created. So making implementation failures harder to program is what misuse resistance is about. So when it lacks misuse resistance, it's easy to do the mistake. So let's look at the doc of Ruby OpenSSL and PHP OpenSSL decrypt. So OpenSSL has implemented those functions, and Ruby and PHP decided to use those instead of developing their own, like other languages did. I'm not saying other languages don't use OpenSSL, but these are the ones I'll be looking at. So you see in the doc, in Ruby, you may additionally need to check that the receive tag has the correct length. What does that mean? And then PHP says the same thing. The length of the tag is not checked by the function. what does that mean? And you can see in the authentication tag of Ruby, there's no mention of the length being basically recovered from the tag we received. So I hope you can see the issue here. Let's do an insanity check. We have some encryption key. We want to encrypt hack the planet. We encrypt the thing with AES-GCM, and this is PHP, but Ruby would be the same thing. Here you can see we have the whole tag that gets generated. Then we take that tag, we take the first byte only, that's what we send, and sure enough, it prints hack the planet. So we've decrypted successfully our ciphertext without the integrity check, or at least it's only 1 byte. It's 256 requests, and we are sure to get the tag. So that's the issue we'll be talking about. So how do you then identify this? Usually you would look for anything that handles encrypted data with OpenSSL AES-GCM. So a cookie, header, whatever. What are these ciphertexts? The way that these ciphertexts are sent, usually it's going to be base 64 or something like that. But when you decode the base 64, you'll see 3 different ways people encode those. So you'll see the JSON, where you'll have nonce, a tag, and a ciphertext. So it's easy in those scenarios to modify the tag to a shorter one. Same for separators, like you'll split on pipes or commas or whatever, and then you'll have the first being the nonce, the other the tag, and then ciphertext. Otherwise, there's the concatenation method that most people do. So ciphertext concatenate with the rest. And so the first 2, obviously, you need to do checks because the tag alone is not retrieved from some string, substring with hard-coded values. And the last method to serialize our ciphertext depends how substrings is implemented. So we'll talk about those checks. So this is bad, there's no check on the tag length. Sometimes I've seen places where they look for the presence of a tag. Obviously, it's not good. We'll talk about string length. If it's 16 bytes, we're good. You've done the check that needs to be done. And then you have substring. So it may seem easy to look at, but it requires an analysis. So we'll go into this. And then we'll go further with that. So when you abstract the tag, remember it's ciphertext, nonce tag, could be tag, whatever. Whatever the order doesn't change, it's just that we know the length of the tag that we expect, we know the length of the nonce, so we're able to extract it with substrings. And finally, the ciphertext is the rest. So if you concatenate a ciphertext length, if the length of the ciphertext is assumed, or the whole thing, well, when you extract values with substrings, you would probably get unexpected values. Let's think of a shorter string that you thought was bigger, and then we'll look into this. So let's look into this. Let's say the data we're sending is nonce, so that's 16 bytes. Then we have CT for ciphertext, and we have A. This is length 15. The tag is expected in the spec to be 16. So we're shorter, the whole message is shorter than only the tag. And so if we retrieve it, thinking the nonce is at the beginning, like this, doing our substring from I to J, we'll get the nonce, and then we'll get ciphertext. But then this data length minus 16 minus 1, well, if we are 15, this is negative. And so we're starting to shorten what we retrieve. And so our ciphertext is CT, and the tag becomes A. And we can do the same at CD because it's moving whatever is being returned. So here we can have only 1 byte for the tag. You might think CT is not a lot for ciphertext. This operates on char positions, not on multi-byte chars. And you can have 4 bytes in 1 char with Unicode. So you would have 8 bytes of ciphertext here, but let's get further. We have the same issue. Here it's substring, length, and starting from I. So the issue is If the length is negative, you'll get a nil, and this will cause issues as well. And finally, PHP, I've seen places doing something like that, which is similar. You substring the nonce, you try to substring, then you have the data remaining, and then you get the tag, and finally you have the ciphertext, which is empty in that scenario. So you can see issues. You have a tag that can be controlled with the length that differentiates. What is accepted in Ruby? What is accepted in PHP? Ciphertext must have at least 1 byte in the Ruby version. So it's going to throw an error because you're not decrypting anything. On the other hand, PHP is allowing an empty ciphertext. You need a tag, a nonce, obviously. But is this useful anyway? Because you'll be bit flipping, nothing doesn't change much. We'll see. So we've seen those, no check. String length is checked, so we don't want that. There's a substring being done, or there's the presence of a tag. So you've got an endpoint. It's expecting a ciphertext. And we've seen that we're missing length checks. What we can do with that, it depends on the context sometimes. But you can do ciphertext forgery, and you can do ciphertext decryption. Again, it depends on the formatting of the plaintext. For forgery, we can apply the same attacks on CTR modes without integrity, because now we can just brute force a tag of 1 byte. And with brute forcing a tag of 1 byte, well, we just need 1 byte to guess 1 byte to be able to do the same things as CTR. Even if we know the whole plaintext or a few parts, and then if we only have formatting knowledge, so I know it's JSON, but I know the data, now we need a bit more. I'll explain why. Let's go with just an overview of CTR attacks. So you find the location of what you know in the ciphertext. So you have some control over what gets encrypted. So let's say I have X in here that I know it's going to be somewhere. I have X here. So it can be either at the end, the beginning, or in the middle somewhere. You know that if you have the complete ciphertext length, you are able to compute where you're going to be if you control enough of what is encrypted. So doing that equation I've put there for you, with 10 A's, the same character, you know you'll always land at this string, substring, whatever, in that position. It's always going to be all A's. Whether that they started before or after, we know those are A's, and those can be flipped easily with CTR attacks. So basically, we find where it is, we flip those with whatever XORs we want to do, and then what we want in that position, and then we brute force the 256 possible tag values. One will match, and then imagine a web server, right? You're sending your cookie, it says you're not authenticated, and then you're trying another tag, you're not authenticated. You try that over and over again, at some point it's going to say, hey, that's a valid cookie. And then, well, it means your ciphertext successfully changed and the tag is valid. That's how you would brute force that tag. If you don't know parts or you don't know much of the ciphertext, there's not much we can do right now. We cannot bit flip. We can bit flip things, but it doesn't mean we don't really know what we're bit flipping, so we cannot be sure of what the value is going to be. So we need to learn their decrypted values first. Or if we control some parts and it takes the first occurrence of the thing, we can maybe nuke the other things with bit flipping that does whatever. But yeah, we need to learn the decrypted values. Now, let's talk a bit about what I call format validity oracle. You've probably already heard of padding oracles. It's similar in the sense that something will be valid, something won't be valid, just like padding, but now it depends on the context. So what you'll be decrypting, the plaintext that is retrieved, ends up being parsed in some way. Maybe it's JSON, maybe it's XML, right? Everybody's encrypting their cookies in XML. But you get the idea. If what you flipped is not valid, it's not valid JSON, well, there's a few characters that can be used to make that character invalid. So now you know whether or not it's valid. So you can assume what value has been used. So like I'm saying, it's context dependent. If it's JSON, it's not the same characters as URL queries or whatever. But basically, you have, for example, this plaintext, user Alice. And now let's assume all these zeros are null bytes, just for the sake of the demonstration, just for things to line up. So if you XOR a character by the same value, it's going to be a null byte. That's the intermediate plaintext. And so if you XOR again that byte with a double quote, it's going to be a double quote in the decrypted ciphertext. And this obviously is not valid JSON. And now you learn that it's whether a double quote, maybe a backslash, something like that. But you have a better idea of what that is. So if it decrypts successfully or not, well, you learn what kind of subset of chars that might be. So you might learn that your guess is valid or in some range. And then from there, from those, you can learn more. We'll get back to this a bit. So yeah. Now let's talk a bit about those, what I'm talking context dependent, those formats. What can they be? They can be anything. I'm not putting them all, but those are things I've seen. So usually it's JSON, it's encrypted, and then gets parsed again when it gets decrypted. It could be a URL query string. It could be raw, but the raw data will be used in some way, and we'll have, in some sense, raw data that is valid, raw data that is not valid. Let's take, for example, compressed data. Well, most compressed algorithms will have a CRC32 at the end, an ALDR32 at the end. So you can use that, like, it's a valid CRC32, so it means it's one of those values, or it's that value. So you can use that in the same way you'd be using a padding oracle. So, a quick overview, if we could give an example in JSON, all the X's can be replaced with these characters, and that's the integer decimal representation of the character. It's not hex, it's decimal. But yeah, in all these positions, you can put, instead of the X, one of those values, and that is going to be valid. The other way around would be invalid. That's just an example. And the obvious values would be, well, there's only a curly brace that can make this valid, or you get the idea. So that is not a range. Now you know exactly if it's valid, it's that value. So now let's use that format validity oracle I've been talking about. And I say use, but I don't have demos because I figured I'd be showing the same thing that the slides are showing. So step one, you pick a guess of a specific byte that might be there when you decrypt. So you apply on the position you want in the ciphertext a XOR of that guess. And once you've applied that XOR of that guess, it should be null. So now you apply whether a valid or invalid value, depending what range is smaller, because you'd be making less requests. And then if you expect it to be valid and it's valid, or the contrary, you expect it to be invalid and it's invalid, well, you need to confirm your guess. Otherwise, it's not a good guess. You go again, you start again. So if it might be a good guess, you keep the same guess. And now the smaller range you have, you try them all. So you XOR by guess and then by the new valid or invalid byte. And if it's still valid, well, you're onto something. And then if all that range matches, it means your guess is correct. And so you've decrypted that byte. Now you go on. Notice that every time you flip the ciphertext with something, you need to brute force a tag. So it's 256 requests per attempt. We'll get to that again. Now, if you have a short ciphertext, remember the substrings, we had no string. And in those cases, even that, you'd not be able to extend the ciphertext. But in the case where you have not enough ciphertext known to encrypt what you want, you would need to add a new byte and decrypt that one and learn that value to be able to flip it. So you append a byte to the ciphertext. You brute force, again, a valid authentication tag for that value. and then you use the validity error code, you decrypt, and then you've learned 1 byte more on your ciphertext. So you have 1 more byte to XOR it with whatever you want. The easy trick with the same methodology, but in JSON, obviously the last char is going to be a curly brace, a closing curly brace. So you replace it, because you know it's a curly brace, you XOR it with a curly brace, with a space, and now there's only 1 character that you can add at the end that is going to be valid, and it's going to be a curly brace. So you brute force the tag for every byte you're brute forcing, and once it's valid, you know you have now successfully added a space and a curly brace. And you repeat that for as many bytes as you need. Now, you might notice there's a limitation here. Sorry. Okay. Well, every time you guess a value, it takes at most 256 attempts for 1 byte to be decrypted, right? Well, finding a tag takes also 256 requests that are done. So for any attempt, you're doing 256. You end up learning a byte every 65,000 requests. It takes a while. And over the network might be long. I know it's doable. It's just not practical enough for a quick demo, but it's doable. Now, so without fast decryption of those bytes, you'll be hard. It's going to be hard to extend that ciphertext that you need to flip if it's too short. But wait, there's more. What is there? I'm trying to remember something I had to say there. Yeah, we'll get to it. Okay. So Panoramix once said, I know you reuse passwords, but please don't reuse anons. What does that mean? What did he mean by this wise knowledge? Have you noticed in what I showed earlier, maybe you have not, but basically the tag length could be 1 byte, but could be 2, could be 3, right? So it only matches the start of the proper tag being the complete tag. So if you have 2 different ciphertexts, how could we have that? Well, we bit flip the ciphertext, and then we brute force the tag. So we now have 2 tags. But wait, you only have 1 character of the tag. But you brute force the first one, and then the second one, and then you get the idea. You brute force the whole tag. You've changed the ciphertext. You have a valid tag. What a nonce reuse is 2 different ciphertexts, 2 tags, only 1 key nonce pair. You're not changing the nonce here. So you effectively have a nonce reuse. So the complete authentication tag of our modified ciphertext can be recovered as well. Let's get back here. So you can do a substring of the tag, brute force it. Obviously, it's going to give hack the planet. Now that you know the first one, you do the same on the second one. Hack the planet, and then 3, and you increment. At the end, you have 2 tags, 2 ciphertexts, 1 key nonce pair. So from there are papers. It's mathematics. GHASH is a polynomial function, but let's not get into that. I think I don't have enough time for that. But basically, you can recover the hash key I was talking about. That hash key being derived from the secret key, the encryption key. Now that we can recover it, if we have 2 tags and 2 ciphertexts, well, we're able to compute any ciphertext. And so I was talking about, let's go with the memes. You have only 1 requirement. So you need 2 ciphertexts and their respective tags for the same nonce. We have that. And so in PHP, remember, the ciphertext can be empty, right? If the substring is not matching. And maybe like you don't have this scenario with JSON that the tag is not checked, or with the separators, you only have substring. What do I do with an empty ciphertext? Well, it can be empty, and it's going to tell you if the tag is valid or invalid. So now you have a ciphertext, which is nothing, and it's tagged, and you have the legit ciphertext, and so you have a nonce reuse. So meaning the substring and stack string issues can be used. The one where I was talking about Ruby, which have 2 characters at most, well, we can do the same thing. We don't need this And the reason we don't need this, we brute force, we have a valid tag, or we could have another, we brute force the tag, it's not required anymore. Basically, we have the G-hash key. So we modify the ciphertext with what we guess. We calculate a corresponding tag, it's going to be the whole tag, but we can do that locally with that leaked G-hash key. And from there, we check the format validity or recall results, and we've decrypted data. Now we don't need 65,000 requests anymore because we don't need to brute force the tag anymore. We just need to brute force what we're decrypting. So, and on average, just it might be the first byte you guess that is right. So on average, you'll get 128 requests for each byte you're decrypting instead of 65,000. This also applies to the 65,000, by the way, so it's not exactly 65,000, but yeah, let's go with that. So now we have our arbitrary length ciphertext that we can flip. So with this arbitrary length key stream that we're recovering one byte at a time with the G-hash key that has leaked, well, the world is ours. We just do whatever we want because it's basically a CTR mode, and there's no more integrity at that point. The G-hash key has leaked. We've been able to do, it's the end, yeah. So conclusion, how to fix that issue? It's quite easy. You check that the length has 16, the tag has a length of 16 bytes, and it should be 16 by default. And obviously, because the G-hash key has leaked, and it's derived from the secret key, well, even if you add the tag length, check. Well, you still have the G-hash key to compute actual tags of that length. So you need to rotate your encryption keys as well. Misuse resistance, just to conclude on that, it can be difficult to detect. When you're looking at documentation, I was actually looking at documentation for documenting something completely different, and I saw that one line, I'm like, no, it cannot be true. No, if I don't know about this, how many people don't know? And actually, I've seen, while searching for that, I've seen 2 CTFs that has done a challenge like this. And obviously, it's not known enough. But yeah, so it's difficult to know if it's missing, and then when you implement your encryption algorithm, like, is it correct? Am I doing the right thing? Is it going to be misused? It's easy sometimes when you're in the code to know that. And to give an example of something else that might be misused that I wanted to include, this is Node.js, but could be, I think there are other places that do the same thing. The authenticity is checked when you do cipher.final. So if you don't do cipher.final, the cipher.update decrypts the data. It sets it to a variable. And so if you do, for example, decipher.update, and then you manipulate that data, you make sure it's valid, and then you do the .final because you've been told you need to do .final. Well, you have an oracle at that point where you've been playing with that data that has been decrypted without the integrity check. So that's another talk for some time else. But yeah, thanks for listening. If there are any questions. Is everybody dead? Brain dead now? No? Any questions? No? Yes.
Did you find it in the wild?
At more than 100 places. Work is still in the progress. And yeah. It's not known. It's really, like 2 CTFs, I've done it. There's a GitHub issue on OpenSSL Ruby since 2016, open for that case. It's here. No, wait, it's here. And the title, I'm not going to click on it, but basically is authentication tag is not checked for length. and they've been discussing in 2016. And the funny thing is I found that issue while seeing code that was well done and had a comment with the link to the issue. So that, yeah, there are some other libraries like Bouncy Castle and C# and others that have the possibility to have an issue similar, but the devs would need to put the tag length, or not put the tag length, but explicitly use the tag length of the tag that has been provided, and nobody does that. So yeah. Any other questions? You wanted to take a picture? All right, thanks for being here.